Significant figures. In this lesson, you are going to identify the quantity of significant figures in the value. Measure an object with precision to show the correct number of significant figures. After a calculation, use the correct amount of significant figures in your answer and understand why significant figures are important. Before we begin, let's see how much you know. Number one, how many significant figures are in each of the following numbers? Go ahead and give me a quantity for each of these 5. And for number 2, suppose a rectangular sheet of steel is measured to be 2.5 meters wide and 3.2 meters long. What is the area of the sheet? Take a guess, and you'll find out the answers in just a minute. First, I'm going to show you how to count significant figures, and then we'll understand why they're important. So what are significant figures? They're the numbers in a measurement that are reliably known, along with one digit which is uncertain. So when you take a measurement, you're measuring length, or you're measuring volume of a liquid, or you're measuring, I don't know, how many grams your cat weighs. It could be any type of measurement. So significant figures, in other words, they're known with precision, and that precision is going to be based on the marks that are on your instrument. So here I have a metric ruler, and the marks go not only to the nearest centimeter, okay, but to the nearest millimeter as well. So this block, for example, could be measured at 5.4 centimeters, but it is kind of in between 5.4 and 5.5. So there is one estimated digit along with your measurement. I'm going to estimate this to be 5.43. So that is my digit of uncertainty. All right, so significant figures are the numbers in a measurement that are reliably known, along with one digit which is uncertain. So before we learn how to apply this, let's take a look at counting significant figures so that you know how many are in each of these values here. So to count significant figures, you're never going to count leading zeros. These are just placeholders. So I'm just going to draw a line there to divide those leading zeros from the non-zero numbers and the trapped zeros in between those non-zero numbers. So this value here has 4 significant figures. 9002 is part of a measurement. Okay, again, for the next one, you're not going to count any leading zeros. Those are just placeholders. This value is measured not to the tenths or the hundredths, but 100,000th place. 100,000. So because this number is measured out to the 100,000th place, the 4, 3, and 0 are significant, meaning this value has 3 significant figures. All right, the third value here is 500.00. So let's say you're measuring, I don't know, the length of a field, and you measure it all the way out to, I'm imagining this is a very, 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 very long measuring tape. It's measuring out to like 500 meters and 0 centimeters, so it'll go all the way to the 500 mark, and the length of my field will not have any distance past 500. It will not go to 501 centimeters. It will not go to 500 meters and even 1 millimeter. No, it's going to be exactly 500.00 meters. That means this value has 5 significant figures. Okay, so remember that significant figures are the numbers that are reliably known, along with one digit which is uncertain. Now this next number here has 3, right? It's measured to the ones place. This value here has 2 significant figures, regardless of the times 10 to the negative 4, which would actually make this value 0.00021 in decimal form. So it has 2 significant figures. The next value has 1 significant figure. Again, do not count leading zeros. Those are placeholders. Next value, 1, 2, 3, 4, 5. Next one, 1, 2, 3, 4. Pretty easy, huh? Next one, don't count the placeholders. 1, 2, 3, 4. Next one, 1, 2, 3. Next, 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. This one, 1, 2, 3, 4, 5. Oh, but what about if there's no decimal here? So this one is a value that says 20,000, but the 20,000 is a rounded value, so we don't know if this is actually 19,999. It's rounded to 20,000. So because there is no decimal, all of these values are part of the rounding. This value is rounded to the 10,000 place. This value has one significant figure. So when you get to values that do not have decimals, you can start on the right side and work your way to the left. These zeros at the end will be placeholders now. This measurement is measured to the nearest hundreds, so it has 1, 2, 3 significant figures. Now let's understand and apply why significant figures are important. As we said, a value that has no decimal is a rounded value. For example, 75,000 people in a city is not as precise as saying there are exactly 74,976 people in the city. So the first measurement has 2 significant figures, and the second one has 5. Okay, now you try. How many significant figures are in each of these measurements above? 230. How many? 2. 230 with a decimal. 3. 230.0. 4. 230.000. 6. 0.0023. 2. 0.0023004. Okay, now that you know how to count significant figures, let's apply. When you're adding and subtracting, your answer, in either case, whether you are adding or subtracting or multiplying and dividing, your answer can never be more precise than any measurement in the problem. Okay, that is the main reason that we use significant figures. Okay, your answer cannot be more precise than any of the values in your measurements. So when adding and subtracting, you are going to round your answer to the lowest decimal place as seen in the measurements or in the math problem. So if you have a value of 431.2 kilograms plus 503.29 kilograms, I'm going to put this in a format that is familiar to you. Here we go. When we add these, I'm lining up my decimal, okay? And I'm saying, okay, the first value here is rounded to the 10th place. That means my answer has to be rounded to the 10th place as well. So when I add these, I get 9, 4, 4, 3, 9, okay? But I'm not going to leave my answer as that. I am going to round it to the 10th place, because my answer here is showing more precision than what I could actually measure in kilograms with my instrument. We can't have that, okay? Your answer cannot be more precise than any of your measurements. So we're going to round this to 934.5. So whenever your value here is 5 or greater, you round up. If it is less than 5, you round down. For the next rule, when multiplying or dividing, your answer should be rounded to the fewest number of significant figures as seen in the problem. Okay, so that's different from the previous rule. Here we have how many significant figures? Good, 5. Here we have how many significant figures? Good, 2. We are going to round to the fewest number of significant figures seen in the problem, so our answer can only have 2 significant figures. When I multiply 65.789 meters times 51 meters, I get an area of 3,355.24 meters squared. Remember, meters times meters is meters squared. So our answer can't be more precise. Now this is telling me that I have my measurement, my meters measured out to the nearest centimeter here, or the hundredth place, but this value here is only measured to the ones. Now I only have two significant figures here. And when multiplying and dividing, I need to round to the fewest sig figs seen in the problem, so I'm going to round this to two significant figures. You might think that you're losing a lot of numbers here, but you're not, because your answer can't be more precise than any of the measurements. Okay, so if I need to round to two significant figures, and this is a 5, that means we're going to round this up. So this is going to be 3400 3,400 meters squared. Let's try a problem. Suppose you wanted to measure the speed of your pet rooster. You would measure the distance it walked and divide that by the time it took to go that distance. So let's say your most accurate measuring device only had a tick mark once every centimeter, meaning it didn't have the little millimeter marks. You find that your rooster walked 2.06 to 2.07 meters, and his toe is closer to the 6 centimeter mark than the 7 centimeter mark. That means you can estimate in between and say it's approximately 2 millimeters. So this measurement is going to contain 4 significant figures. Using an old pocket watch, you measure his time to be halfway between the 4-second mark and the 5-second mark, so your best estimate is 4.5 seconds. So you take your two values, and your answer is a very long decimal, and do not write all of those digits. You're going to round to two significant figures. This value is an 8. It's greater than, it's 5 or greater, you are going to round up. So this is going to be 0.46 meters per second. All right, let's see how you did. How many sig figs are in each of the following? The catch was this last one here. Whenever you have an exact count of something that's not going to have a fraction involved, like you can't have half of a penny, for example, you can't have a third of a penny. You're going to have exactly 100 pennies. That type of value is infinite. So it's 100.000 repeating. So if you wanted to say like 100 pennies times 27, for example, you would use this as your number of significant figures because infinite is greater than 2 sig figs. So this one has an infinite number because it's 100 pennies, and this has exactly 2 significant figures. So your answer should have 2 significant figures. Okay, number 2, we just wanted to see if you could apply the rules of multiplying. So 2.50 has 3 sig figs, 3.2 has 2 sig figs. What would you round your answer to? 2 sig figs. Read through why significant figures are important so that you have a deeper understanding. This is a review of what we just went over. Now, I want you to take a minute and do practice problems 1 through 56 here. And for the first part, you're going to count the number of significant figures. For example, there is 1 sig fig here, 1 sig fig here, etc. Then in 51 through 56, apply your addition, subtraction rules and your multiplication, division rules. Pause the video here and come back when you're done to check your answers. And go. Welcome back. Let's see how you did. Number 3, how many? 1. Number 4, 1. Number 5, 1. 6, 2, 7, 3, 8, 4, 9, 2, 10, 3, 11, 4, 12, 5, 13, 7, 14, 1, 15, 1. So what I'm doing here is not counting any zeros that are leading if there's a decimal, and I'm not counting any zeros that are trailing if there's no decimal. 16, 2, 17, 3, 18, 4, 19, 1, 20, 2, 21, 5, 22, 4, 23, 7, 24, 3, 25, 4, 26, looks like 6 there, 27, it's rounded to the thousands, 3, 28, rounded to a million, 1, 29, 6, 30, 3, 31, 1, 32, 1, 33, 1, 34, 4, 35, 3, 36, 2, 37, 3, 38, 3, 39, 3, 40, 5, 41, 4, 42, 6, 43, 1, 44, 4, 45, 4, 46, 2, 47, 5, 48, 3, 49, 6, 50, 2. Okay, 51. On 51, you may have calculated 8, 6, 3, 6, 5. You need to round that to the tens position. That's a 5, so you're going to round up, and you have 8, 6, 3, 7, 0. 52. Your answer should be rounded to the tenths position. So when you calculate, you get 707.12. And when you round that to the tenths position, it's 707.1. 53. You're rounding to the hundredths. You may have gotten in your calculator 991.991. You're going to round that to 0.99. 54. Adding 100 plus 90, you get 190. The value with the lowest decimal place is the tens place, and that is already at the tens place, so no change is needed. 55, you are multiplying these two values together. In the calculator, it gives you 108.357. You need to round this to 2 significant figures, not 4 significant figures. So 108 is going to round up to 110. So 110 is your final answer. Okay, you can't go, you can't just drop it off at like 108 because that's 3 significant figures. You're not going to round up to 109 because that decimal there is a 0.3, so you can't round up, but the next highest unit you can round up to is in the tens position, so your answer here is 110. Okay, 56. When you divide these two together, you get 29.984. You need to round this to 2 significant figures. Could I leave it at 29? Well, this next value here tells me I need to round up, so I need to round up to 30. Now that only has 1 significant figure. And if I put 30.0, that has 3 significant figures. But what you can do is what we're going to learn next is put this value in scientific notation. 3.0 times 10 to the 1. because the coefficient here at 3.0 indicates the number of significant figures. So 3.0 has 2 significant figures, which is what we want. And the times 10 to the first power is the multiplier, making this value equal 30. All right, I hope you learned a bit. For those of you who are still a little on the fence, go ahead and read through Tutoring Significant Figures, and this will help you review what you just learned. Great, don't forget to do your assignment on Schoology, and I will see you in the next lesson. Have a great day. Bye.